Hello, welcome back. In this video, we'll discuss the crystal oscillators. Before understanding what crystal oscillators, let us try to learn certain things about the oscillators in electronics. An electronic oscillator is an electronic circuit that produces a periodic oscillating electronic signal, often a sine wave or a square wave or a triangular wave. These oscillators, they convert direct current, that is the DC, from the power supply to an alternating current signal. An electronic oscillator is an electronic circuit that produces a periodic oscillating electronic signal, often a sine wave or a square wave or a triangular wave. These oscillators, they convert the DC, the direct current from the power supply, into an AC signal. And the signal can be in the form of a sine wave or a square wave or a triangular wave. Essentially, it is an electronic circuit. And this electronic circuit produces oscillating electronic signals, and the oscillating electronic signals are produced by converting the DC power from the power supply. They produce the AC signals. The oscillators generally use the RLC circuits or the tank circuits in various combinations of R, C and L. The examples for the oscillators are Colpitt's oscillator, Hartley oscillator, Pierce oscillator and phase shift oscillator. In fact, not only these four, there are many electronic circuits that can work as an oscillator. In these oscillatory circuits, we use the RLC, and most of these oscillators, they operate in the audio frequency. So if you try to design them to operate at radio frequency, then they fail to produce the same frequency, or frequency is not stable. When you design one of these oscillators to operate at the radio frequency, we find that the frequency is not stable. Further, whenever an oscillator is under continuous operation, the frequency stability gets affected. So the continuous operation affects the frequency stability. The factors that are responsible for the frequency stability are the power supply variations, changes in temperature, thirdly, changes in load or output resistance. Whenever a variation in the power supply is seen, due to which one can also find a change in the frequency, or the frequency is said to be drifting. A change in temperature will cause a change in the parameters of the inductor, capacitor and also the resistance. As a result, also one can find changes in the frequency, or the frequency no longer remains stable. Changes in the load also affects the frequency. To overcome these problems is to adopt a piezoelectric crystal in parallel resonant circuits, which provide high frequency stability in oscillators. So the use of piezoelectric crystals in parallel resonant circuit provide high frequency stability. We know that piezoelectric effect can be seen in crystals such as quartz, Rochelle salt, tourmaline. They are the examples for the piezoelectric materials. Very largely, quartz is used in crystal oscillators. One of the reasons is quartz is abundant in nature and it can easily be handled. Now we shall discuss briefly about the quartz crystal and how it is going to be used in the crystal oscillators. Quartz crystal has hexagonal structure. The quartz crystal is cut into small slice, and the quartz crystal can be cut into X cut or Y cut crystal. We have already seen what is piezoelectric effect. So now we shall see the working of quartz crystal. In order to make the quartz crystal work in an electronic circuit, we place the quartz slice or the quartz crystal slice between two parallel plates. These are the two parallel plates. And these two parallel plates, they form a capacitor. Whenever an AC voltage is applied to the quartz crystal, the crystal starts vibrating. And these quartz crystals, they have what is known as natural frequency. The frequency of the applied AC signal is equal to the natural frequency of the quartz crystal. Then the vibrations will reach a maximum in the quartz crystal, because due to the resonance, lot of energy is absorbed by the quartz crystal. Since we have a quartz crystal between two parallel metallic plates, we can have an equivalent circuit for the quartz crystal. Equivalent circuit of the crystal is the equivalent circuit of a crystal in an electronic circuit looks like this. A crystal in an electronic circuit is represented using this symbol, that is two parallel plates between which you have a rectangle, and its equivalent circuit consists of an LCR in series. This is one branch of the equivalent circuit, and this will be in parallel with Cm, that is the capacitance of the capacitor. So you have a series of LCR branch, and this will be in parallel with a capacitor Cm. Here, when the crystal is just mounted and not biased, then the capacitance will be equal to Cm. When the crystal mounted across the AC source, it acts like a tuned RLC circuit, because by using this Cm, we are tuning this RLC circuit. Now we shall look at the frequency response of the crystal. This is the frequency response of crystal, and here we have the reactance along the Y direction and frequency along X direction. So if you plot along the X direction the frequency and the reactance along the Y direction, then you call it as the frequency response of the crystal. There are two resonant frequencies that are very close to one another. The first one is the series resonant frequency, represented with an Fs, and this occurs when the reactance of the inductor, that is L, is equal to the reactance of the capacitor. And under such conditions, the frequency is given by Fs is equal to 1 over 2 pi square root Lc. And the second resonant frequency will be there, which is represented with an Fp, that is the parallel resonant frequency. This occurs when the reactance of RLC branch is equal to the reactance of Cm. The crystal offers a very high impedance to the external circuit, and the frequency of the oscillation is given by Fp is equal to 1 over 2 pi square root Lc sub r, where C sub r or Cr is equal to Ccm upon C plus Cm. Since Cm is very large, so Cr can be approximately equal to C. So thereby we'll have closely spaced two resonant frequencies for the crystal. Now we shall see the crystal oscillator circuit. The crystal oscillators generally can be constructed in a number of ways. However, the transistor PS crystal oscillator is the most commonly used crystal oscillator. Transistor PS crystal oscillator, most commonly used. So this will have a potential divider network that is produced using the resistors R1 and R2. You have a transistor here, you have a bypass capacitor CE, and you have a blocking capacitor C. Since the capacitance of the crystal is quite large, the small variations in the temperature, they will not affect the performance of the crystal. Thereby we get stable frequency from the oscillator. We shall see the advantages now. The crystal oscillators have a high order of frequency stability. The quality factor of the crystal is very high. The disadvantages are, the first one is the crystals are fragile and can be used only in low power circuits. Secondly, the frequency of oscillations cannot be changed appreciably. In this video, we have discussed the crystal oscillators. Before understanding what crystal oscillators, we have briefly discussed the oscillators. An electronic oscillator is an electronic circuit that produces a periodic oscillating electronic signal, often a sine wave or a square wave or a triangular wave. They convert the DC from the power supply into an AC signal. The oscillators, they use RLC circuits or the tank circuits. We have seen the examples: Colpitt's oscillator, Hartley oscillator, Pierce oscillator, phase shift oscillators. These oscillators generally they work in the audio frequency. But if you try to design these oscillators to function at radio frequencies, further continuous operation of these oscillators will lead to drift in frequency, or the frequency becomes unstable. So continuous operation affects the frequency stability. The factors that affect the frequency stability are the power supply variations, changes in temperature, changes in load and output resistance. To overcome these problems, the crystal oscillators are to be designed. The crystal oscillators, they use the piezoelectric crystals in parallel resonant circuits. They provide high frequency stability. Piezoelectric materials are quartz, rochelle salt, tourmaline. They are the examples for the piezoelectric crystals. Quartz is generally used in crystal oscillators because quartz is abundant in nature. Quartz has hexagonal structure. The quartz crystals can be cut into X or Y cut crystals. One can produce X cut or Y cut crystals from the quartz crystal. So a thin slice of the quartz crystal is used. Later we have discussed the working of quartz crystal. A thin slice or a wafer of the quartz crystal is placed between two metal plates. These are the metal plates. And the quartz crystal will have a natural frequency. When the applied AC bias frequency is equal to the natural frequency, then due to resonance, maximum amount of energy is absorbed by the quartz crystal. Maximum vibrations can be seen in the quartz crystal. We have seen the equivalent circuit of the quartz crystal. We have said that we'll have an LCR series branch in parallel with a capacitor CM. We have also seen the symbol for the crystal in an electronic circuit. We have seen the frequency response. We have said that there can be two different frequencies. One is Fs, that is the series resonant frequency, which is Fs is equal to 1 over 2 pi square root Lc, and this can be seen only when the reactance of the inductor is equal to the reactance of the capacitor of the LCR branch. Fp, the parallel resonant frequency, can be obtained when the reactance of RLC branch is equal to reactance of Cm. So Fp is equal to 1 over 2 pi square root LCR, where Cr is the resultant capacitance, that is equal to CCM upon C plus Cm. Since Cm is very large, Cr will be almost equal to C. Thereby one finds closely spaced two resonant frequencies for the crystal. We have seen the crystal oscillator structure. We have said that transistor PS crystal oscillators are widely used crystal oscillators. In the circuit, you have a potential divider network produced using R1 and R2. You have a crystal, you have a blocking capacitor and a bypass capacitor. There are two advantages. The first advantage is they have high order of frequency stability, and the second one is they have high quality factor. As a result, frequency is stable and well defined. Disadvantages are the crystals are fragile in nature and they can be used in low power circuits only. The second disadvantage is the frequency of oscillations cannot be changed appreciably. Thank you.